I'm so happy to see many of you here again. Hi, I am Ines. I'm a computer science student. This is our very second session, and I appreciate the commitment that some people are showing to actually, and the enthusiasm they are showing to be here on Sunday evening. So I will start sharing my screen. Yeah, I think you're seeing, right? Yeah.
No, you start sharing, but immediately stop sharing. So
Oh, okay, sorry.
Try one more time. Super.
Okay.
Now we can see recursion on your screen. Yes, now we can see your screen.
Very nice. Thanks, Anna. Well, I welcome you again to our second session. Well, I will start with a quick recap of what we did last week. Basically, first we defined an algorithm as a set of rules that are applied to an input in order to get an output. Then we discussed why algorithms are closely connected to data structures and how actually choosing the right data structure defines the efficiency of our algorithm. And also we explored these data structures, which based on arrays, matrices, linked lists, stacks, queues, and all. And what are we going to cover today? This is the question of today. Basically, we will see algorithms. Well, we will start with the question of why are we learning sorting? Why sorting matters? Well, basic sorting is everywhere, starting from the CPU on your laptop. It's always scheduling tasks. Also, data packets in networks are sorted before transmission. And actually, even when online products sorted by price or reviews. So sorting algorithms are a fundamental problem, and they have many, many applications. And we will start today with bubble sort, which is one of the easiest. The list goes on. Yeah. The most well-known sorting algorithms fall into two categories: comparison-based algorithms and non-comparison-based algorithms. Small spoiler, we will try to cover both in today's session. We'll start with the bubble sort. So how actually bubble sort works, we basically take two neighbors and we start comparing them with each other. And it depends on how you want to sort your array in ascending order or descending order. So if one of the neighbors is bigger than the other, then we just swap them. And why it's called bubble sort? Basically because in each round, the biggest element will be bubbled to the end of the array. And as an algorithm, or I wrote it actually as a Python code. I don't know if some people will hate me right now because some people like JavaScript or Java, but I prefer Python at this time. So when we write the bubble sort, it's written as follows. We basically just define the length of our array, and then we have two nested for loops, and each time we go through the array and compare to the two neighbors. And then the question we will be asking, how long does it take to get the job done? Or if you ask it more appropriately, because last time we've seen that the efficiency of an algorithm is based on its time complexity. So if we reformulate the question, we will have how efficient is the sorting. Well, you will be asking me, how do we calculate the efficiency? Well, efficiency depends from how much time it takes. So logically speaking, we will measure its runtime. So you might think, okay, let's just check how much time it takes, and this is it. Well, I run the same sorting algorithm, and this time I run the bubble sorting algorithm 2 times, and each time it gave me a different runtime. So same algorithm gives me different runtimes. And that's actually problematic because me and you, we will never agree on the time complexity of an algorithm. And so we will never know which one is more efficient. Is it my algorithm or yours? And actually, the reason why the runtimes are different, it's because runtime depends on the hardware and also on the other processes that are running on the CPU. So the idea was to have a universal measure of efficiency. And we thought, instead of just calculating the running time that the CPU is using, we basically just measure the number of operations, how the number of operations scales with the input size, independent from the hardware. And this is where the Landau symbols come into role and into use. And that's why I'm gonna, in today's session, I'm gonna introduce 3 of them, which are the most commonly used and most important as well, I find. Yeah, the first one is the big O notation, which measures the upper limit of an algorithm, and it's actually it describes the worst case of a scenario of this algorithm, and it's also known with big O of f of n. So it's a function of n, and it describes how basically the runtime scales with the input size. Second, there is omega, which is kind of the opposite of big O, and it measures the minimum time taken by an algorithm to execute. So big O is actually for worst case scenario, and omega is for the best case scenario. And it's also written in function of n. And what comes between the both of them is theta. So this measures the average time taken by an algorithm to execute, or the lower bound and upper bound at the same time. So it's called theta because it's also at the size of our thumb. So the function take a thumb size to run. And now going back to our question, how fast is bubble sort? Well, basically, if we analyze the code I wrote in Python, well, it will also look similar in other programming languages, don't worry. Basically, we have 2 for nested loops, and each one of them go into, in worst case, or also in average case, in this case, n times. And this actually happens in constant amount of time because we're just swapping 2 elements. We don't need any extra running time for them. And as a result, we have big O of n multiplied by big O of n, and then multiplied by big O of 1, which gives n multiplied by n multiplied by 1. And at the end, we get just big O of n squared. The thing is, n squared is okay. And you might think also that, okay, yes, now I can sort any array I want, and n squared will do fine. But the thing is, it's very, very slow. And I brought this meme. It's you versus the guy she tells you not to worry about. So n squared and n log n. And to deeply understand the difference between the growth of these functions, let's see this plot. This basically analyzes the number of computations in function of input size. The best one and the most optimal one is constant amount of time, of course, big O of 1. Then we have the logarithmic one, then linear, log linear, quadratic, and the worst case, which is factorial. And it happens when we permutate elements, basically. It's the number of permutations in total. So the question that we always ask, can we make it faster? This is our goal. We want to write efficient algorithm. We don't want to just solve problems, but we want to solve them in the most efficient way we could. And the answer is actually yes. And this is where I introduce merge sort. How does merge sort basically works? Merge sort, it basically takes, we start splitting our array into two subarrays, and the splitting goes on and goes on, and this process is actually called dividing. And then we start conquering. We basically because we divide our our array till we reach an array with just one element. Then we take just these one by one elements and start to comparing them and also merging them at the same time. And the code for that, this is dividing, and then we start conquering to have the array at the end. And the code for it looks like this. It might look a bit complicated, but it's super simple. You just start defining the middle of an array, and then you split it, and then you keep splitting recursively on both sides. And probably the question is, how fast is merge sort? The problem is with bubble sort, it was easy to analyze how the time complexity actually works because of simply seeing the amount of steps each for loop takes. But here, since we have recursive calls, it's not really easy to tell. And that's why we need to analyze this kind of tree that is created when dividing, and basically the same one is created when conquering but reversed. And as we see, we have the main call, which is C of n, and then we divide them, and we have two calls of C of n by 2. And in order to solve this kind of linear recursion, we will need something called master theorem. Well, master theorem says the following. If we have a recursive function, which usually in this form, T of n, has m calls of T alpha n plus theta of n nadir power of k, with alpha is a number strictly between 0 and 1, m is a natural number, which is the number of calls, and k is a real number. And then basically we have 3 cases, and we just analyze the behavior of the alpha is at the power of k. Basically, if it's less than 1, which means this whole term is growing very, very slow in comparison to this term, and that's why the whole recursive function grows with theta of n at the power of k. Else, if it's equal to 1, which means these both are growing equally, then we have a growth of n at the power of k log n. And then if it's bigger than 1, means this part is growing much, much faster than this part. And that's why we need to calculate a c, so that at the end, our T of n is in theta of n at the power of c. And then if we apply the master theorem at our dividing and conquering algorithm, we will basically have this recursion call, T of n equals 2T of n by 2 plus theta of n. How is that exactly? Basically, we have 2 recursion calls because each time we divide the problem into 2 subproblems, which are 2 arrays. And then each subproblem is the size of n by 2, because first array is the size of n. Then if we divide by 2, then the second 2 arrays are of size n by 2, and so on and so on. And plus theta of n, basically because merging takes a linear time of step. Linear time, yeah. And if we apply the rule on how to analyze the final time complexity of the recursive function, basically we will have it as 1, which is the second case in the master theorem. And that's why T of n is growing at n log n. So we started a few minutes ago with a sorting algorithm that goes by n square. And now we landed some sorting algorithm which goes much, much faster at n log n. The thing is, merge sort actually have a sibling, which is quicksort. They both have the same logic of dividing and conquering, but quicksort tried to be special from his sibling merge sort, and we are scientists decided to name it as partitioning. So merge sort actually divides and uses extra arrays, but quicksort divides and do in place merging. That's why it's slightly different. And then how does merge sort actually work? We basically, well, there are many variants of this algorithm. Basically, if you are choosing a random pivot or a pivot as the first element of the array or a pivot as last one, in the variant I am using right now, we basically using the pivot as the median of the array, which will give us the best performance and the best time complexity. So we start by choosing the pivot, which is the median in our case, and then we start partitioning the array into two arrays. Basically, we check all the elements that are smaller than the pivot, then we put them at the left side, and all the elements that are bigger than the pivot, we put them at the right side. The code for quicksort looks as following. We basically, as said here, we take middle element with indices of low and high minus low per 2, or actually you can use this in dumb way, which is hard-coded, or you can actually calculate the real median of an array, which also the time complexity for the median calculation is big O of n. So it stays under the boundaries. Now, how to calculate the time complexity of quicksort, how fast it is. Basically, since partitioning has the same logic of dividing and conquering, we have the same function basically, but with different descriptions. We have two calls because each time we split into two halves. And then the partitioning this time also takes big O of n, because basically each time we take the pivot, we go one time through the array and check all the elements that are smaller and all the elements that are bigger than the pivot. And at the end, we get the same running time, which is n log n. And the question right now, can we make it even faster? Well, the answer is yes, but not really. Till now, we have seen three sorting algorithms: bubble sort, merge sort, and quicksort, and they are both using comparison. They are comparing elements. Now we will see something, I will call it a bit creative. It's not really easy to come up with the idea. Even when I studied the algorithm, I found it super amazing, very interesting to see, which is counting sort. Basically, we have this array, which has 8 elements, and then we identify the max element. What is the maximum? By the way, these are the indices, and here are my actual elements, just to let you know. Well, the max element here is actually 5, so we create a new array which has 5 elements, and as initial value, all of them have 0. And then we start iterating on our initial array and see the number of occurrence of the element. For example, the 0 came 2 times, and then the 1 came 0 times in our array. The 2 came 2 times. The 3 came 3 times, and etc., etc. So each time you are seeing the indices of this array and checking the number of occurrences in the original array. So after having this array, start manipulating a bit. This part, which I found super interesting actually, because I thought of it in other ways. In this part, we basically make the summation of every neighbors to see for example, for example, if we have 2 zeros, then where is the indice of 1? When does it come? So it comes actually 0 plus 2 times. So it comes in the second position. And for the 2, it comes 2 plus 0 plus 2. So it comes at the 4th position. So we have 2 zeros and then 1 comes at the position 2, which basically we don't write it, and then 2 comes at the first position, so we have to choose. I know at the start it might be a bit complicated or not really understandable, but just I will leave the slides for you so you check them later. It's actually simple. So back to the story. You just summate the number of your currency of each index, and then you start the real sorting, which is really, really magical. You start from the end of the array. So we start with indices number 8, so which is element 3. And then we check in our counting array, we check for the element 3 with the index 3. So it's right here. And then it has the position, initially it has the 7, but we write it at the 7th position, and then we do -1 here. And then we go on, we go to, oh, sorry, I missed one. Yes, exactly. And then we go to the element, which is 3, and we check again 3, and it's at position 6. So we write it down, and then we do so now it's 5 and not 6 anymore. And then we go to the next element, which is 2, and then we check the element with indices 2, and then it's 3, where it was 4, so we write it at the position 4, and then we do -1, so it became 3, and so on and so on. And magically, at the end, we get a sorted array just by counting the number of the currency of each element and then writing it down. So at the start, we had 2 zeros, so we wrote down 2 zeros. We had also 2 twos, so we write the 2 twos, then 3 threes and 1 5. And basically, that's it. That's where the magic happens. And now the big question. How the whole code looks like. It's basically you choose the max value of the initial array, and then you utilize a new array with zeros and with length of the max value +1. And then basically the whole approach we just saw, we just apply it right here. We start by thinking how many times the number occurs in the array, and then add it to the count array, and then start from the end and just write our elements down. And questioning how fast is counting sort? Well, basically choosing the max value is a O of n time, so it's linear time, because you will go through the whole array and see the maximum. And then creating the new count array goes with O of max val. And for the others, it's basically here for the while loop, it's also O of max val, and for the for loop, it's also O of max val. So at the end, we will have a O of n multiplied by k, and k is actually our max value, so the maximum value in the original array, which is pretty much faster than the others. And if k is actually smaller than n, then we will have big O of n. So sorting will be done in linear time, which is super nice and super handy. But since we can do sorting in linear time, why are we actually seeing all the other sorting algorithms, from merging to quicksort to, there are also insertion sort, selection sort, and heap sort, and many others. So why don't we just use the counting sort? Why isn't really that popular? Well, basically, it takes too much memory. For example, suppose you have 1,000 numbers ranging from 1 to 1 million, and so your k, which is your max value, is 1 million in this case. So the count array will be really big. So it won't be only using a much more bigger time complexity, but also the space complexity won't be really efficient. So it has a huge waste of memory. And second, it can't really handle floating numbers or complex data. For example, it can't really handle strings, characters, and also negative numbers, since we calculate each time the number of occurrence of each element, so it won't work for negative numbers. And for example, if I have this array with those names, Alice, Bob, Charlie, and David, and I want to sort them with alphabetic order, well, it won't work simply. And sadly, that's why counting sort is not really much used. Yeah, and as a summary, I brought this table which summarizes all the things we have seen. So the bubble sort takes, in worst case, big O of n square. Merge sort and its sibling quicksort both take n log n, while quicksort, as I said, just in this variant when the pivot element is actually the median. Since, for example, if it's the first element or the last element, and for example, your array happens to be already sorted, then sadly, the worst case scenario will be also big O of n square. And for the counting sort, big O of n plus k, and k is the maximum value of our initial array. And then the space complexity, basically bubble sort doesn't need any extra memory. We don't need any extra arrays or any data structures, so it's big O of 1. Merge sort needs extra arrays because we are dividing each time and creating new arrays, so it's big O of n. Quicksort takes less memory, which is big O of log n. And counting sort basically takes just, we create the count array, which is big O of k, which is our max value. And then the use cases, bubble sort is dedicated for small database or just educational purpose if you want to start learning bubble sort, but please don't use them in your interviews, in your coding interviews, because they are not really impressive. Just use merge sort or quicksort, and which are also used in sorting large databases, and they are very stable and very familiar. And our leftover counting sort, basically, it's nice to know the whole algorithm is very interesting, as said, and creative, but no, it's not really used and it's not really helpful. So what are we gonna see next week? Basically, we will see graphs, and we will delve into the graph theory and a lot of amazing stuff. Stay tuned. I want to thank you for your attention for this session. I hope it was informative, light also, because I know it's Sunday evening, and yeah, I try to always keep it light but also informative, but just keep in mind you are here just to seek inspiration, and this is not all about sorting. In the internet there are many other amazing algorithms. I'm just giving you the motivation to go and search for them. And let's connect. This was it for me. I hope you enjoyed it. Thank you so much for your attention, and probably till next week. But if you have questions, feel free to ask. Yeah.
I checked chat. We haven't questions. We have just a lot of thanks, Ines. So that brings us to the end of today's session. Thank you all for joining and actively participating. We hope you found today's discussion insightful and gained a deeper understanding of the key concepts we covered. So we explored today sorting algorithm. We connected this concept to real-world applications. Thanks for your examples. And a huge thank you to Ines for sharing your expertise with us today. It's Sunday evening. You have exams. It's super busy. And biggest thanks from my side that you agreed to be part of these sessions every Sunday.
And it's my pleasure, Anna. I'm also so happy to be your guest, and I'm so happy to share my knowledge and also my motivation.
And it's really very important today. So Not only you dive into sorting algorithm, today you cover big O notation, which is a fundamental concept for every programmer. I can tell from my own experience as programmer, big O, when you join junior, you don't care about big O notation. But after you start thinking about this, it's really a fundamental concept for every programmers, even junior today, should start thinking about big annotation. Understanding time and space, real complexity is crucial for writing efficient code. Our main task is to write efficient code, and we truly appreciate your insights.
Thank
So
you so much. I just want to add a small thing. Actually, writing an efficient code isn't just showing how an amazing developer you are, but also it's really sustainable. And it's basically writing green software, because the less the time complexity and the less the space complexity you are using, the greener and more sustainable your code is. Because so at the end you are actually helping the nation with great technology and great software, and at the same time you are saving the planet. Because don't forget that each CPU runtime and everything that leaves footprints, and also each click you do on web pages and all that harms the nature. So writing efficient code is our responsibility, not just a goal.
yes, we can help. Don't make our planet so warm soon.
Yeah.
We should care about each other and our planet. So,
Yeah.
okay, as this session was recorded and will be shared on our YouTube channel, I send link on our chat. Once again, a big thank you to everyone for being part of this session. Big thanks, Ines, for being with us and preparing super informative and super short session. Looking forward to seeing you all in the next one. Until then, happy coding and keep learning.
Yeah. Ciao. Till next week.